So far we have seen that you can write current expression, mass balance expression for a given mechanism, and then assuming pseudo potential static mode, that is we have a DC potential and we superimpose a AC on top of that. We have expanded that in Taylor series, some cases we have expanded in Fourier series, and we have obtained expression for current. Then we have taken the ratio of current to the potential, or potential to the current, call it as impedance, current to the potential, call it as admittance. And later we have also seen that when you apply large amplitude perturbations, still pseudo potential static mode, it is possible for us to use numerical method, in some cases Taylor series, some cases Fourier series, but in general numerical method to solve these equations and predict the current oscillations, do the Fourier transform and predict the impedance. And in corrosion experiments usually people use pseudo potential static mode. In batteries, in fuel cells, usually the EAS experiments are done in galvanostatic mode. That means we have a constant current and on top of which we ask the instrument to apply a sinusoidal current and then monitor or record the potential, and then it performs the FFT on the potential measured, or potential required to maintain that current, and then we take the vector ratio of potential to current and call that as impedance. Now, when you apply a small amplitude perturbation, if it is a constant potential or constant current, for a given DC potential there is a DC current, and if you apply a small amplitude perturbation, whether we conduct the experiment potential statically or galvanostatically, we will get the same impedance spectrum. When you apply a relatively larger amplitude perturbation, there is no one-to-one correspondence between these two spectrum. Now, using these numerical methods, it is possible to simulate or model how a given reaction will respond if we perform the experiments in galvanostatic mode. So, I want to show you two examples. One is the simple electron transfer reaction, next is a reaction with adsorbed intermediate, and as long as you know how to handle these two, you should be able to handle any general mechanism. So, the outline, we want to apply a sinusoidal current and measure the potential at omega. Basically it means we will apply Fourier transform and then look at the magnitude and phase at the fundamental, okay, and then calculate the impedance. First I want to look at the case where you have a double layer capacitance with a Faradaic impedance in parallel. Current that goes through the top double layer capacitance is denoted by IA. Current that goes through the Faradaic impedance we call it as IB. What we measure or what we control is the total current. We can't tell this much current has to go through double layer capacitance and this much current has to go through Faradaic impedance, because when we measure we do not even know what the double layer capacitance is and we do not know what the Faradaic impedance is at any given frequency. When we do the simulation, we assume we know the CDL value, we know the Faradaic impedance or the expression for Faradaic impedance. So, the current that we control is IDC plus IAC. IAC here is IAC 0 sin omega t. So, in the notation now this is something we control, this is an independent variable. We can also say the total current can be visualized as Faraday current plus double layer current. IA here is the current through the double layer. So, the current through the double layer we can write the expression, it is CDL dE by dt, potential across this is the E, and Faraday current of course is a function of potential. When we add these two, we should get the total current that we apply. So, in general we would write CDL dE by dt plus f of E is IDC plus IAC 0 sin omega t. Now, potential is something we are going to measure or potential is something we have to calculate here. Under steady state conditions, that means DC current and DC potential, the capacitance will not allow any current to pass through that, okay, because dE by dt is 0, E is a constant, dE by dt is 0. Therefore, we can take this expression and simplify it, that is going to show f of EdC is the same as IdC. Now, let us say we consider a reaction, very simple electron transfer reaction, only forward reaction is considered here. For this particular case, it is easy to write the steady state solution. I can rearrange it and say IF by Faraday constant K10, that will give me e power B1e. If I take natural log on both sides and then rearrange, I can say EdC can be calculated for a given set of parameters and given IdC value. Of course, this is valid only when we are in the very much positive direction, when potential is much above the open circuit potential. At open circuit potential, current will be 0 and reverse reaction cannot be neglected. This is a DC potential corresponding to the IdC. If you apply an AC on top of the DC, this E, potential E, will also have a DC component and a variable component. It may be sinusoidal, it may have higher harmonics depending on the value of IAC 0. If it is small, we can say this is also going to be sinusoidal, we can neglect the higher harmonics. If it is large, we will not be able to neglect the higher harmonics. But anything that is changing, we call it as EAC here, and average we call it as EDC. So, we need to take the total current and solve this equation. This is a first order non-linear ordinary differential equation. Okay. Dependent variable is E, independent variable is T, and starting point is at time t equals 0, potential is EDC. It is a non-linear equation. We will have to use numerical integration to solve this, but it is fairly straightforward. You can use MATLAB solvers such as ODE45, ODE15s, or you can use any other programming language, or you can write your own solver. So, just as an example, for simple electron transfer reaction for a given set of kinetic parameters, here K1 is written as 10 power minus 5 moles per square centimeter per second, exponent B1 is 20 inverse of volts, double layer capacitance is assumed to be 10 microfarad per centimeter square, and if we use a DC current of 1 milliamp per centimeter square and apply AC of 10 microamp per centimeter square, first we calculate the DC potential, and that is 117 millivolts versus OCP, that is nearly 100 millivolts above OCP. It is probably not a good idea to neglect the reverse reaction, but we will go ahead with this story anyway. Once you know the DC potential, one can calculate the charge transfer resistance. In this case, charge transfer resistance and polarization resistance are the same. They happen to have the same value. Faraday impedance is independent of the frequency, therefore, charge transfer resistance and polarization resistance are the same, and that comes to about 50 ohms centimeter square. We can solve the ordinary differential equation numerically for various frequencies and then calculate the impedance. What we calculate here is the total impedance including the double layer capacitance. So, whatever we calculate out of this equation will give us E as a function of t. We subject that to Fourier transform and write the E as E equal to E0 plus E1 sin omega t plus phi 1 plus E2 sin 2 omega t plus phi 2 and so on. And we take E1 by IAC 0 as the magnitude of the impedance. We take phi 1 minus 0 because we give the current the time at t equal to 0, we say it is EDC, and after that this is the expression which describes the current. So, phi 1 minus 0 gives us the phase of this impedance. So, if we plot the complex plane plot, we would get a semicircle as you would expect. 10 microamp centimeter square is a very small value. So, under small amplitude perturbation you would get a clean semicircle, even under large amplitude perturbation you would get a semicircle, okay, for this particular mechanism. What happens when you have a more complex mechanism? We look at the mechanism with intermediate species, two-step mechanism. We have seen the mass balance equation and we have seen the charge balance equation before. So, mass balance equation is gamma d theta by dt is k1 1 minus theta minus k2 theta, and the current equation is f k1 1 minus theta. Only the first equation contributes to the electrons. Under steady state condition, this we replace E by EDC, I by IDC. This of course under steady state condition d theta by dt goes to 0. In this particular example, it is possible to rearrange this and write a clear expression for EDC. In general, when you have 2 or more steps, it may not be possible to do this, and you will have to solve these 2 equations simultaneously. See, we do not know EDC, we do not know theta SS in this case. So, 2 equations, 2 unknowns, it is possible to solve, but they are not linear equations. So, these are non-linear algebraic equations which you have to solve simultaneously to find EDC and theta SS. You may have mechanisms with 2 intermediate species. You will have an equation for theta 2 SS, theta 1 SS, and then an equation for EDC. All of them should be solved simultaneously. In general, you have to use numerical method. This particular case, I can replace k10 e power b1 EDC into 1 minus theta SS, which happens to come here also, with IDC by f, and then I can write theta SS in terms of IDC by f 1 by k2. So, once we know the k2 value, once we know the kinetic parameter value and IDC, of course, we know the Faraday constant, we can estimate the theta SS. And once you know theta SS, you can rearrange this equation and write the expression for EDC, but in general you may not be able to do this. Now, if you apply sinusoidal current, I take the general equation, which is current through the double layer and the current through the Faradaic impedance is going to be the total current, and of course, mass balance equation remains the same. Now, these are differential equations, nonlinear differential equation. Independent variable is time, dependent variables are E, potential E and theta. So, we will have to write it as dE by dt equal to, on the right hand side, some function of E, theta and t. Second equation is d theta by dt is some function of E, theta and t, and then use a programming language or programming environment with initial condition at t equal to 0, we need to specify what is the value of E and what is the value of theta, and then ask it to integrate. Whenever we have a mechanism with intermediates or even without intermediates, if you have significant solution resistance or you have significant mass transfer impedance, all those cases, even for a simple electron transfer reaction, in the previous case where you have used pseudo potentiostatic mode, we know that we have to apply potential, wait for some time, let it stabilize and give a steady periodic result, and we can take that result. If I take data before that, it is not going to give me correct value of impedance and it will not be KKT compliant. Similarly, here we have to wait for some time, let the potential be steady periodic and then take data. So, I want to show you an example. We will take this 2-step reaction with single adsorbed intermediate. We have the kinetic parameters like this, that is K10 is 10 power minus 9 moles per centimeter square per second. The exponent B1 is 19.47 volt inverse, and that is essentially saying alpha equal to 0.5. K2 is likewise given here and the gamma value is given. We take a DC current of half milliamps per centimeter square and an AC current with an amplitude of 0.2 milliamp per centimeter square. Now, when we apply this DC current plus AC current, the potential will oscillate, the baseline will change, and after some time it will settle. In this case, it settles after 10 milliseconds for this set of kinetic parameters and this mechanism. Okay. And to integrate these equations, we need to use ODE15S. Basically, these equations are stiff equations. And after going through the process of integrating, getting the potential, performing the Fourier transform, and then taking the ratio of E1 by IAC 0 and calculating the phase minus 0 phase for the current, we can calculate the impedance, and if you plot, this is what we get for an AC amplitude IAC 0 of 0.2 milliamp per centimeter square. Now, the same equation you can use it with a larger amplitude. You do not have to do anything differently, you just have to follow the same procedure. I also want you to note the following. Look at the impedance values at low frequencies, it is a little more than 200 ohm centimeter square. Okay. So, if we take the impedance value magnitude as roughly 200 ohm centimeter square, and then the applied current has an amplitude of 0.2 milliamp per centimeter square, the amplitude of this potential oscillation, it is going to be roughly 40 millivolts. 40 millivolts is usually not considered to be in the linear regime. One has to verify by changing this amplitude and seeing whether the impedance at any frequency is independent of this amplitude. But in general, if we say 10 millivolt, people normally believe that it is likely to be in the linear regime. If we say 40 millivolts, there will be questions. Regardless, here if we change it from 0.2 milliamps per centimeter square to 0.4 milliamp per centimeter square, what happens? We run the same code, get the spectrum, and you can see this is little more than 200, this is the low frequency value or p value here is more than what we got in this case. So, this is close to 300, more than 250, this is probably less than 250, and likewise the charge transfer resistance is little more than 100 ohms centimeter square here, and this is probably little higher value here. You can see that there is a difference. So, nonlinear effects do come in. Of course, it is possible for us to simulate and estimate or calculate what one would get under galvanostatic AS measurements for this particular reaction and for set of kinetic parameter values. Now, a question. Okay, earlier when we analyzed with potential static mode or pseudo potential static AS measurement, we showed that you can start with Taylor series, expand to few terms, truncate, and then rearrange and write it in Fourier series, or in some cases you might be able to write directly in Fourier series and get the components fundamental, second harmonic, third harmonic, and so on. Now, can we do that here for the galvanostatic measurement? In order to do that, earlier we always wrote current as a function of potential, and then we changed the potential. We said this E is going to be EDC plus EAC, and we could write this in Taylor series by expanding around EDC. So, we would write this as x plus h, where x is the equivalent of EDC, h is the equivalent of EAC, and then truncate after certain number of terms, rearrange, etc. Now, in order to do the same thing here under galvanostatic measurement, we should be able to write first potential as a function of current in general, and then say this can be written as IDC plus IAC for our sinusoidal current variation, and then say I can expand this in Taylor series, rearrange, and so on. The problem is, in most of the cases you will not be able to do this. If we have a very simple electron transfer reaction at low frequencies, it is possible to write this in terms of certain functions called Lambert W functions, and that has been published in 2012. But in general, if we take any reaction, it is not possible to write like this. It is not possible to write an explicit function E as a function of current. So, as an example, if you consider this reaction of M going to M plus adsorbed plus electron, M plus adsorbed going to M plus solution, we call the first one as K1, second constant as K2. This is what we have seen few minutes ago. The governing equations are given here. First is a nonlinear ordinary differential equation. It is written in terms of the dependent variable E and the dependent variable theta. The second equation is also an ordinary differential equation. It is written in terms of theta, and of course, K1 is a function of potential, K2 in this case is independent of potential. So, this is a coupled differential equation, nonlinear ordinary differential equation. We do not have an analytical solution for this. In most of the cases, we will not get it. So, it will not be possible for us to write E as a function of I, which case we will not be able to expand in Taylor series or write in Fourier series and so on. Whereas, numerical method can be applied in all cases. It is going to be time consuming to write the code, it is going to be time consuming to run the code, but you will get a clear answer for the nonlinear galvanostatic measurement. Next, what happens if solution resistance is there? It is not negligible. Now, this is easy to handle in case of pseudo galvanostatic measurement. Okay. One, potential drop across the solution resistance is easy to measure. You can go to high frequencies, measure the impedance. This is in complex plane plot. You can fit this part to resistance, a capacitor or a constant phase element, and a resistor, as long as we are in the high and mid frequency region, not low enough frequency region. In any case, it is easy to measure the solution resistance. In simulations, we do not have to do anything differently. We assume that solution resistance is not playing a role. We do not even worry about the solution resistance in the calculation. We can use the same circuit and calculate the potential across this interface without worrying about the solution resistance. So, for an applied current, which is IDC plus IAC, we can calculate the potential across the interface based on our model. We know this is double layer capacitance, we know this is a Faradaic impedance, and we have an expression relating the potential to the current. So, we can calculate the potential across the interface. When we do experiments, we measure only the total potential across this system. So, it includes the solution resistance. What we measure is the sum of E plus E1, or we can call it as E interface plus E solution. Now, E solution is easy to estimate. We know the solution resistance, we know the current we are applying, therefore, E solution can be calculated. Now, we know the total measured value, and we can calculate the potential drop across the resistance, across the solution. So, we can calculate or estimate what is the experimental value for the potential drop across the interface. All that we need to do is compare the model prediction for the E interface with the experimental value of E interface, and if they match, we can say that model is probably a good model to choose. So, in terms of calculation, in terms of simulations, we do not have to do anything differently. In terms of experiment, we need to measure the solution resistance and we need to measure the total potential drop across this system cell, which is what normally we would get from the potentiostat. So, handling solution resistance is lot easier when we are doing the calculations in the galvanostatic mode. So, in summary, using numerical method we can simulate pseudo potentiostatic experiments, we can also simulate pseudo galvanostatic experimental measurements. Okay. In case of potentiostatic measurements, if we have simple electron transfer reaction, we do not have a differential equation, at least for the cases we have seen till now. Okay. In case of pseudo galvanostatic measurement, you will have a differential equation to solve, but then as long as you are using numerical method, it is quite possible to solve. Taylor series and Fourier series expansions are not that easy or not possible in majority of the cases. Okay. So, numerical simulation is pretty much the only method as far as I know that you can use to handle or model pseudo galvanostatic measurements. And in this case, solution resistance effects are easy to handle, at least compared to what we had to do in case of potentiostatic measurements. Okay. We will stop here today.